Ballereau. I come from Jena Optronik, and I would like to share some experience we have made when porting our ASTRO APS platform from the GR712 to the GR740. First of all, I will make a few words about Jena Optronik itself and the product portfolio, and then we'll go into a bit more details about the platform itself, the previous platform or the current platform, the APS2 platform, and the new one. Then I will go in a bit more detail about experience we made using when porting the software, particularly the improvement we have seen and also the new complexity, and then a few closing words. On Jena Optronik itself, we are a company located in Jena in Germany, 240 employees approximately. We are a subsidiary of Airbus Defence and Space. As you can see on the right-hand side of the slide, our three main markets are North America, Europe, and Asia. There is a small list of customers of us. Our products are meant to address needs in several areas. We have five main product lines. The star sensor product, the ASTRO product family. Star sensor are navigation devices for satellite and spacecraft, taking the stars as reference. We also have camera systems and camera that can be used for navigation, for instance, and also LiDARs. These are laser scanning devices used mainly when docking, for instance, on the ISS or on a satellite for space maintenance. We also have space optics and electronics and services. In my presentation, I will go in a bit more detail in the first three categories as they share a common platform. This common platform is first based for our Star Tracker product. This is our family of Star Tracker. On the left-hand side, you have the previous product, ASTRO 15. It's still flying a lot. And you have also ASTRO APS, our current product, already flying as well. And already first extension with gyroscopes, ASTRO Gyro. On the top side, you see our new family of product. We have not just one product for this next generation, but three to address the constellation market and also the mark needing a very, very high precision, extra XP. But our main product is an evolution of ASTRO APS. It is called APS3. This APS platform is a platform for small device. Star Tracker are no large devices. These are really small. You can get them in your hand. This is really, the bevel is better protruding, but it's a really small device. Internally, this is based on the GR712 processor with a small amount of memory and a small amount of non-volatile storage. And to fit many customers' needs, we have a high modularity on the hardware side. Also, power converter can be modular from 28 volt, 50 volt, 100 volt, depending on the customer, and also the communication side is very flexible with SpaceWire, MIL1553, and others. This modularity is on the hardware side. This is very easy with the GR712, which is packed with a lot of interfaces internally, and for those that are not internal, we have extra FPGA to support them. Also, with our small form factor, we cannot have, this is not a large computer where you change boards. We still have modular building blocks inside it, also to cope with the use in not just Star Tracker, but also in LiDAR devices and navigation camera. Also they are not sharing PCBs themselves, the common blocks are the same. And to cope with this modular hardware, we need also a modular software to be able to exchange parts easily. We have a large common part and also a modular protocol stack. If you see on the left-hand side, this is ASTRO APS or APS2. And the evolution on the right-hand side, this is APS 3. It's even smaller than previously. It's based on the GR740 with more memory and also a larger amount of non-volatile storage. We also rely on multiple communication device. I have to precise, just as before, we don't use all these communication device at once, but we are exchanging either a different board or a different fitting of the board, assembly of the board. We select from for each customer which interface will be used. Only one is functioning at once. Because we try to we have to be extensible and modular. And we try to have a large common part. This common part is very constrained because it has to support every possible extension as much as we can foresee. In this new platform, to spare volume, power, thermal dissipation, and because of the added power of the GR740, the extra FPGA is only optional. A star tracker is sensible to heat because the optical device, the high-precise optical device in it, is sensible to thermal effects. And without the FPGA, we do the processing with symmetric multiprocessing in the GR740. This is done using ARM6 as operating system. It has been space qualified thanks to ESA, and we use the same modular software. Now I will go a bit more in the software, but also in not that much detail. We have seen on the bottom part, the hardware is modular. We have processors that can change, different memory fitting, different communication devices, and on top we have different, depending on the product, also different application. And in the middle we have a large amount of generic software. We have first a large set of platform services, a lot of telemetry, telecommand handling, and also services, for instance, for in-orbit software update or for test are shared in these common services. The protocol stack, I said earlier, is also modular because we have to cope with different communication interfaces. And beside the operating system, we have a large hardware abstraction layer that help us to separate the hardware from the rest of the application. This layer is basically defining abstract interfaces, and several instances or several implementations of these interfaces have been performed over the year, and it has now been ported to the GR740. As there are common roots between the GR712 and GR740, it has been possible to reuse or to use as basis previous drivers for the development of the new GR740 drivers. The rest of the software could be used as is. This was the goal, to isolate the changes in the hardware abstraction layer, and we were able to use the old software on the new platform. I want to highlight that the available test board from Geissler are very, very useful when doing early prototyping and testing of the platform. These are tools we greatly appreciate. Being a software guy, I will now go in a bit more details. In experience, we have found when porting the software and improvement we have found in the new GR740. Previously in the GR712, every controller has a fixed interrupt level assigned in hardware. This is the same for interrupt generated from a GPIO pin. If you have a modular platform where you tend to exchange one communication device for another one, or an hardware component for another one, this was sometimes a bit inflexible to have this fixed interrupt level, as the priority is bound to the interrupt level. Now with the GR740, it is a lot more flexible. You have the possibility to each controller has an internal bus line, and you can assign the interrupt level for this bus line. This is also true for the GPIO. So for a modular platform, when you want to move all everything from time to time, this is a great increase in flexibility. In some situation, you need a very accurate timestamping of some event. This can be a flank on a synchronous signal, or a reception of a packet, or a time code. And receiving these times is always bound to an interrupt signal. But interrupt have latencies that are really hard to characterize. This is both on the hardware side and in the operating system side. So you add sometimes a larger and precise timestamp. Now with the GR740, you have your timestamping unit. You can get a very accurate timestamp when an interrupt was asserted. You can make use of it to get not just a timestamp, but also to assess the overall latency, both on the hardware side and in the operating system. This is a very valuable improvement. As we have seen already in other presentations, there is now 4 cores and a wider bus, and there is also a large level 2 cache. This level 2 cache is a really nice improvement for performance. You have to make sure your application is using cache effects, locality in time and space, and provided you do so, you get a really large improvement. The internal scrubber is also helping that you don't have to flush it periodically to prevent a buildup of errors. This is a good improvement. Another improvement is in the GPIO controller. A GPIO controller is using, basically, you handle this with a register with bit mask. Every pin has a bit, and you usually only are interested in one pin. Reading the value of one pin is easy, but if you want to modify just one pin without modifying the others, this gets complicated in software. You have rest condition. You can another signal can be changed, or another controller can do something. And if you do it in software, you have rest condition. The GR740 is adding new manipulation register to do some operation on this bit mask, and so you can clear or flip or set a bit without risk of doing anything wrong. This is a nice improvement. The interrupt polarity register would have been nice as well for some of our users, but already this is a nice improvement. As we have seen already, just like on the GR712, there are a large number of integrated controllers. For our modular platform, we are a lot of interest to have as many of them integrated into the processor. We have to fit FPGA for the ones that are not integrated. And many of these controllers have been improved. This can be a small improvement, like the FIFO for the UART has been made longer, or the Ethernet controller is a larger improvement with gigabit internet. These are nice improvements. Still, there are some constraints. You can't use every controller at once. This is for us usually not a problem. You just have to pay attention to the pin multiplexing. Many controllers have DMA channels, so really nice to handle. For SpaceWire, there are a larger set of improvements. First, there are more ports, as we have seen, and there is also an integrated router. For those who have already experience with a previous product, like the GR712 or the 18-port GR718, this is now all integrated and quite easy to handle. Still, you need to modify your drivers to make use of them. And also, a controller has been added for hardware support of the SpaceWire time distribution protocol. There are also another kind of improvement on the GR740, but unfortunately some of them are not so usable on our platform. For instance, the dual-channel SDRAM controller is fine if you can afford to use dual-channel. This needs more space, more volume, you need more chips, and if you don't need that much memory, this would be also wasteful to have twice or 4 times as much as memory as you need just to have the bandwidth. So in some applications, you prefer to do with the old bandwidth. This is a bit unfortunate. DDR would have been really fine, but I understood this was not possible at the time. The memory scrubbing has now received support in hardware. This is a fine addition. It can work automatically, repeatedly. Basically, you can program it and it do everything. Unfortunately for us, with a small amount of memory and a quite busy memory bus, it's a bit too fast and a bit working in too large bursts. So it tends to disturb some timeliness effect that we see. So it's a bit unfortunate, but it's like this. I will now go in a few words on new feature or new aspect of the GR740 that brings new or extra complexity. We have seen there are many buses or large buses in the GR740. There are also many buses. There are 5 in total, and there are special rules for the error propagation that you have to cope with. And if you want to make your error detection, identification, recovery process, you have to get a global overview of the status of the whole system. This is a bit more complex as before because the status is shared in many components, and yes, you have to handle this extra complexity. The IOMMU bridge is for us not much relevant as we don't do time or space partitioning. We are more interested in the ability to route traffic away from the processor bus and directly to the memory bus. But doing so opens another kind of problem with cache coherency problem. And if you want to deal with this, this is again added complexity. So you either have to see how you better handle offloading your processor bus or handling more complexity. And as we said earlier, there are 4 processor cores. This is not directly the GR740, but the fact that we have to do symmetric multiprocessing, and as every SMP application, critical, embedded, this is not the easiest kind of software to compute or to write, to test, validate, and justify. I said earlier, we're using RTM6 that has been qualified thanks to ESA, and we're quite happy with this. Another complexity is in the bootloader. We are using our own bootloader, and we had to do some extra changes. We don't use the standard clocks from the GR740, and to change the clocks, the PLLs, change clock multipliers, more precisely the PLLs, this is done in software. And if you change the PLLs, then the CPU is resetted again. This is something your bootloader has to handle. This is not that complicated, but this is a change. SMP start, if you are using SMP and your bootloader was not handling this already, is also something you have to change. A last point is the PROM bus and pin multiplexing. We are using parallel PROMs on the PROM bus, and the MIL1553 that is for us very important is not, I would say, a first-class citizen, but is on this PROM bus and shares pin with the rest. And if you use it, you cannot use the all widths and the all address possibility of the PROM bus. This is not black and white alternative with small or wide or nothing at all. You have a lot more flexibility, but using also this extra flexibility to get every single pin possible for your PROM bus is more complicated in software and in hardware. And I already come to the end of my presentation. As you can see already, the update from the GR712 to the GR740 is mostly straightforward. Basic support can be done quite quickly, quite easily. And but as usual, better tuning for a new processor that complex is a lot more complicated. Also identifying bottlenecks and small changes that sometimes have a wider impact is not always easy. And even more complicated is sometimes using a new feature. To be able to use new features on improvement, you need some time to drastically redesign your software. And this is a barrier to reusing legacy software. And last but not least, now the SMP conversion is in itself a large effort. But overall, the GR740 is a really nice improvement over the GR712. Thanks for your attention.